So these are some review slides. You've already seen this. This was the one-dimensional filter. This is two-dimensional filters. The only reason I'm repeating this over here is so that you will have proper copies for your notes. Okay. This was the CNN where we looked at the mapping. Then we looked at a 3-color image. Then we looked at K filters. Then we specifically looked at the number of parameters. All right. This is where we stopped last time. And we said that as you have parameter sharing, okay, so if you can see this, this is the parameter sharing. It reduces the number of parameters by W2. Okay, W2, if you remember, was the size of the activation window, the size of the output. Okay, so what that means is that if you're doing parameter sharing, and you always do that. So I haven't seen any CNN algorithm which doesn't do parameter sharing. But there was a time when people didn't do it. So this was an improvement in the original algorithm. So basically then the number of parameters becomes a lot smaller and it becomes independent of the input size. It only depends on what? On the filter sizes. So it's filters times filter squared multiplied by what's D1? The depth of the input. So if it's 3-dimensional, that's 3, okay? And then it's multiplied by what? By the number of filters. K is the number of filters, okay? So F squared D times K is the number of parameters. So this is an important equation that you need to be aware of, so that we will be looking at this as we look at examples, okay? So now let's take a look at examples. This is an example which is available online. Let's take a look at it online as well. So this is from a course which is taught at Stanford. It's a very famous course, CS 231N, okay? And I would encourage you, whenever you get a chance, take a look at it. All the material is available on YouTube. It's actually taught originally by Fifi Lee, who is one of the pioneers in this field, okay? And she's the one who started the computation ImageNet, and many of her PhD students have gone on to do wonderful things, okay? So this is an example of a convolutional neural network. And let's take a look. So you can toggle this and you can look at it in more detail, but let's take a look and try to understand this, okay? So I've copied this from there, and let's try to understand what's going on over here, okay? So what we need to figure out is, let's say that this is an input, okay? This is a particular image, okay? So this is the input over here, and the input consists of, can somebody try to explain to me, what do you think are all of this on the left side, which is in blue? Is that the filter? That should be that's the input, okay? So the left on the blue is the input image, okay? These two in the red are the filters. So these, as the label says, are the filters, and this is the output, okay? So this is the activation map, which is the output of the CNN, okay? Now, let's try to figure out the parameters. What do you think is the size of the input, and what do you think is the padding size? So what do you think is W1 and H1, which could be the height? So padding size is +1, okay? So +1 basically means that this is the original input, okay? So what would be W1? W1 is 5. H1 is the same as W1, it's a square input, all right? So this is also 5, okay? The pad is equal to 1, okay? So what would be W2? What is the input? What is the filter sizes? What's F equal to? 3. H1 is simply the height. So H1 is this from here to here, okay? And W1 is from here to here. Okay, this is W1. So W1, H1 is the same. The padding is over here. So the whole size of the input becomes slightly bigger. It becomes 7 by 7. The filter is of size 3. Okay. The stride, they haven't specified the stride somewhere. Do you see the stride somewhere being specified? Stride seems to be 2. Okay. So let's go back over here and see. Let's toggle the movement. Size stride is 2. You can see that, right? This is jumping 2. Okay. So the stride is 2. Filter size is 3, and the stride is 2. Okay. So what should be the output size? W2 would be equal to 5 plus 2p, which would be another 2 minus 3 divided by 2 plus 1, right? So what should that be? 5, 6, 7, 4, 2 plus 1, that should be 3. So does that make sense? The output is of size 3 by 3. Okay, so this so far so good, right? Now let's try to calculate, let's try to see if the output calculation kis tarah se ho rahi hai. How do we actually calculate this 1 over here? Okay, so this is a 1. Let's see how this 1 should be calculated. Can somebody tell me how this 1 would be calculated? आपकी बताइए, multiplication कीजिए किस तरह होगा? So let's say we take this filter. Now, how many filters do we have? We've got 3 filters over here. Are they identical? No, they're 3 different filters. And you've got another 3 filters over here. So आपके पास के जो number of filters है वो क्या है? Is it 6? Let's go back to what we talked about. Yeah, but if you look at the filters, what do you think K is? Remember, look at this picture. Can you tell me what K should be? What is this picture telling you? K should be 2. Who said that? Right. And why is that? Those separate filters हैं, right? लेकिन ये 6 क्यों हमें नजर आ रहे हैं? Because of activation, नहीं? Huh? The answer is right in front of you. Sorry? So देखें, आपने आपका sorry नाम क्या था? Mahmood has said that K is equal to 2 in this particular case, right? So he's saying here is one K and here is another filter, right? But what about this? Is this one filter or is this many filters? So it's the depth. So there are 3 separate filters because the depth over there is what? Is 3. So it's an image which is of 7 by 7, but the depth is 3. Okay, because it's red, green, and blue. There are 3 colors. So for each one of the red, green, and blue, you have a separate filter, and you have 2 completely separate filters. Okay, so let's go back over here. So this is your first set. जो मैंने वहाँ पर दिखाया था इस तरह का filter. This is the first set of filters. Okay, and this is the second set of filters. This is simply equal to the depth D1, which is equal to 3. Simply because यहाँ पर 1, 2, and 3 है, red, green, blue है. तो इसी तरह आपके पास 3 filters होंगे which correspond to the RGB. Okay, but you have a completely separate filter. K is equal to 1 and K is equal to 2 separate filters. And what do you think these 2 filters? Why are you trying to have 2 separate filters? And why you have यहाँ पर जो 3 filters इनका क्या मकसद है और ये इनका क्या मकसद है? What do you think they're trying to do? Why do you have this structure? So ये जो filters हैं, they are trying to look at the RGB, right? So they're trying to see a particular image and they're simply trying to see कि उस image के अंदर जो red, green and blue में जो फर्क है वो क्या है, right? Now you could have a separate activation map for each one of these. Theoretically, yes, you could. So you could have actually 6 output maps. But practice is that you don't have 6 output maps. You have a single map for all 3 of the RGBs. Okay. Why? Because from practice they found it doesn't make sense to have 3 activation maps for the 3 different colors. Okay. So this is what the practice is. Doesn't mean this is cast in stone and you cannot come up with your own algorithm, but this is what the practice is in most CNN algorithms. What they do is they use a single activation map and they do a sum over all the 3 colors. Okay. But sorry. And the output, yes, then it becomes very good, is in grayscale. The output, the activation map is not in RGB, is not 3 colors, it's in grayscale. Okay. And it's a combination of the 3 different colors. Okay. So now this particular output is sort of a combination of the 3 different colors. And this particular filter, what do you think is the difference between these 2 filters now? Is there a fundamental difference between these filters? If you look at the activation map over here, and you look at the activation map over here, do you think that it will be looking at 2 different, do you expect any major difference between these 2? What are they going to be focusing on? Different features, right? These filters will not be looking at different features. They'll probably be focusing on the same feature, but they're looking at slightly, the variation in color. But these 2 will be fundamentally quite different, all right? This filter, this set of filter, this filter, and this filter will be quite different. Ho sakta hai ki one of them may be looking at one completely different feature, and the other filter k is equal to 2 will be looking at a completely different filter, okay? So when you look at the activation map, you'll probably get an idea as to what the k is equal to 1 filter and k is equal to 2 filter are looking at, okay? And we'll take a look at some examples as well so you get an idea, okay? Now let's do the math, okay? Let's try to see how is the output over here calculated. Can somebody help me calculate this one? How do you think this one is calculated? So what we're going to do is we're going to put this particular filter. Where are we going to put it? Well, we're going to put it over here. We're going to start with the top left corner and we're going to calculate the result over here. Okay. So can somebody do a quick calculation over here? What do you get if you multiply it? You'll get 0 simply because this entire thing is 0. All right. So you get 0. Okay. Now this is not 0. This is 1. Why is that? Because we have to actually look at the second filter as well. So this is going to be a sum over all the RGBs, okay? So let's do the multiplication over here for these 2. What are you going to get? So the only 2 values are this over here. This becomes a -2 and then a +2. And then there's a 2 over here that becomes a -2. So this is a -2 over here, okay? So this is the output over here is 0. The output here is -2. Let's do the last one. What do we get? So you get 1 -1. Then you have a 2. Then you have a +2. So you have a +2. Okay. So if you add all of these up, what do you get? You get a 0. Why do you think this is still not a 0? This is a 1. Sorry. We have another filter. Which one? This one here, k is equal to. But you see, this is going to create a separate activation map. This activation map is going to come out over here. So this particular one is simply on the basis of the first filter, okay? But why do you think the output is still not 0? Well, when you place a filter after over here, when you place it over here, when you do a stride of 1, where do you think the output is going to go? The output is going to go here. Okay, so that's not going to answer your question. There's something else on the screen which is going to give bias. Very good. So I'd highlighted it as well. You can see that there's a bias. So remember, the bias is added after all the convolution layers, all the filters are multiplied. You add the bias to the end. Okay, and notice that there's only a single bias. Okay, so this entire filter has only one bias. Okay, and that's a 1. So you add a 1, which is 1, and so the answer becomes +1. Okay, so you get a +1 over here. Okay, let's do one more quick example over here. Well, I'm not going to spend too much time. So you can calculate this. Okay, how will this be calculated? You will actually do multiplication over here and here, you multiplication here, here. What will the bias be in this case? It will again be 1, right? Because there's a single bias over the entire filter. And if you do the multiplication, hopefully you should be able to get 5, okay? I would suggest that you do these maths. It's simple, trivial arithmetic, but it's important to understand the CNN, how the CNN algorithm is going on, okay? So this was the first example. This is a fictional example completely, and this is from the example, as I said, from the core CS231N. Okay. Now, so far we've only looked at a single layer. Okay. Now, what happens when you add multiple layers? Because remember that was a neural network. That was not a neural network. That was not a DNN. It was a shallow neural network. Okay. But if you get into deep neural networks, obviously you're going to have layers cascaded, as you've already seen in the earlier example. Okay, so what happens when you add multiple layers is that, let's say this was your first layer, okay, that had a filter and that had an output. Okay, so this was the output of the first layer. The output of the first layer, the activation map of the first layer, becomes the input of the second layer. Okay. The output, the activation map of the second layer will become the input to the third layer and so on. Okay. So this becomes the input of the second layer. And then you'll have a bunch of filters over here and so on. And you'll have another output. And then this will become the third layer and so on. Okay. So that's the basic idea. And now what we'll try to do is we'll try to look at a slightly more complex example. Okay. So this is an example which is available again online, and let's take a look at it online. So I've given you the link at the bottom. This is a site which has been developed by one of the very famous people in this particular area, and they've used a data set which is called the CFAR10. Okay, so this is the Canadian something algorithm, it's a data set. And as you know, a lot of the work in deep neural networks was done in University of Toronto, okay, under Jeff Hinton, all right, Jeffrey Hinton. And this was one of his PhD students who worked on this, and he created a data set. And there's a CFAR10 data set, and there's also CFAR100, okay? The CFAR10 data set basically has a total output of, well, it has 10, it tries to decide one of 10 categories. Okay, so if I look at what a CFAR10 looks like, so if I open it up over here, you'll be able to see that it has basically these 10 different categories. Okay, so they have quite a large number, it says 5,000 images, and these have already been labeled into one of 10 categories, right? Airplane, automobile. So there's some things, and then there are some animals, birds, cats, deers, dogs, frogs, and so on. And again, trucks and ships. Okay. So this is a very simple data set, not too complex. And the idea here is that they're going to apply an algorithm, and you can actually tailor the algorithm. Okay. So I just started this a little while ago before the class started, but let's say if I wanted to restart it. I could start it over here, and you can see that it immediately starts working. I can clear the graph, and I can start it off so you can experiment with this. So you can pause it as well. You can clear the graph, and then you can say that, what should be the learning rate. Okay, you can specify the learning rate. It's sort of similar to TensorFlow Playground, but different as well because it applies it to real images. Okay, you can choose the momentum parameter. All right, people remember what momentum was. Okay, you can use a batch size. Remember, where does this come from? Stochastic gradient descent. So all the things that we've already talked about are coming in together. There's a decay factor, a weight decay as well. There's something that perhaps we haven't really talked about. And then here's the actual network. So you can write your own network, okay? And this is, I think, written in, it's not written in TensorFlow. I'm not sure. I think it's written in PyTorch or some other language. Probably say, sorry, it's in JavaScript. Okay. So, so here's the algorithm. It's fairly straightforward to decode. What you can see is that the first input layer, it's taking inputs of size 32 by 32. Okay, so the image sizes are 32 by 32. The depth is, the image depth is 3, which means it's in red, green, blue. It's three colors. Okay. The first hidden layer has a filter of size 5. Okay, so SX implies the filter size. The number of filters is 16. Okay, so earlier our number of filters was 2. Here the number of filters is 16. Okay, the stride is 1. Then there's a padding of 2, so that's being put around the filter, around the input, and the activation it's using is ReLU. G. Okay, so that's the architecture. So there's no answer to why. They simply picked a magical number. All right, you could pick a completely different number, but this is an example of an architecture where they've used 16. All right, picked it out of a hat. So okay, that's slightly wrong what you just said. There actually be how many filters? Sorry, 16 times 3. So the total number of filters, the total number of weights will be how many? Remember how we decided that the number of weights will be? Yeah, it's actually F squared. Okay, so it's F squared times depth times K. Okay, so let's take a quick look at the number of filters which we looked at. The number of filters, but number of parameters is F squared times D times K, which is basically the number of weights. Okay, so every filter will have a weight associated. Every filter pixel will have a weight. Then it will be multiplied by the depth multiplied by K. Okay. So so coming back over here, the number of filters, this is K. All right. K is what you're controlling. Can you control F? Where are you controlling F from? F is over here, already specified. Are you controlling the size D1, the depth? No, you're not controlling that because that's already given. That is the input. So if the input is already given, the depth of the filter is already given. Okay, but you can choose the number of filters. Now the question is, how many filters should you choose? And what should be the basis of choosing the number K? What do you think should be the basis of choosing K? Sorry? This is not the output. This is actually this is the input layer. Okay. The output of the input layer, that's why it's showing as an output. Sometimes it's confusing. That's why it's important to understand the way the things are coded. This is the output of the input layer. Okay, so the input layer is of size 32 by 32. Okay, and it is of depth 3. Now, my question was that how would you choose the number of filters? And what are the trade-offs? What happens if you choose only one filter? What do you expect? Less features. So you won't be able to actually look at different features because आप पे एक ही feature पर focus करें. What if you make f too big? What if you make k too big? You make k 100. Sorry, computation cost would become very large because as you saw that the number of parameters is proportional to k. So you could make k reasonably large, but not too large, okay, because there are more parameters as well. So every layer will have a number of parameters, okay. So they've chosen k to be 16 in this case, not too big, not too small, okay. So basically what they're trying to do is, in the first layer, you're trying to look at 16 features, okay. So they picked 16 features. They're choosing a stride of 1. So in this particular layer, you're not going to be, so in the early example, we were choosing stride of 2. What was that doing? That was actually reducing the image size, okay? But why do you think they're using a stride of 1 over here? Can you look at the next layer? What do you think the next layer is? That's max pooling, right? So the max pooling has got a filter size of 2, right? And it's going to use a stride of 2. Okay. So basically the next layer is going to, what is it going to do? It's going to reduce the size. So if the next layer is doing the work of reducing the size, you don't need to actually do it twice. So they've separated it out. They've said, okay, in the first layer, I'm going to keep the stride 1. I'm not going to try to reduce it. I'm going to focus on the filters. And I'm going to, in the next layer, I'm going to try to reduce the size. Okay, so that's a combination of these 2 layers. Activation is ReLU. Why are they using ReLU and not, what's the other one? Sigmoid. Why are they not using ReLU, you think? What's the advantage of ReLU over sigmoid? So we talked a little bit about it. Sigmoid, there's a problem which, okay, so we'll talk later about it. I haven't spoken too much about it, but ReLU, I said, is a popular solution, and it has a very distinct advantage, which is called that it avoids the vanishing gradient problem, okay? I don't think we've talked about that. We're going to talk about it today. So ReLU is very popular, and this is what's being used. The next layer is a max pooling, okay? It uses a 2 by 2, so it's going to, it's not very large, but it's going to basically look at 2 by 2 and it's going to reduce it by factor of 2, okay? Next layer, as you can see now, this is being repeated, okay? This is, what's the difference between the next 2 layers and the first 2 layers? Number of filters has been increased. So instead of using 16 filters, the next one uses 20 filters. Again, everything else is the same. The max pool, is it the same or different? It's the same. So it's again applying a max pooling layer. Okay. Let's look at the third layer. Okay. So it depends on how you calculate what is a layer. Okay. So you could say the first layer is a convolutional layer, the second layer is a pooling layer, the third layer is a convolution layer. Or you could say that the first 2 layers is basically the first layer, and then you've got a second layer, and each layer has a convolution and a pooling, convolution, pooling. It depends on how people call it, all right? There was a question, G. Filter का जो size है filter का K? जी. Right. So that's going to be automatically calculated. Remember how we're going to start it off. When we start it off, initially it's going to take random weights. Okay, so the filters, the weights here are the filters. All the weights will be completely random. Okay, all the filters will be completely random. Even the bias will be completely random. Ji. Right. That's the magic. Okay, that's the whole magic of deep learning. All of this happens through what? back propagation. All right. So back propagation is such a wonderful technique, and this was again the innovation in 2012, which made the whole field of deep neural network come in. And that again was Jeff Hinton from University of Toronto. That was a great idea. And in fact, back propagation concept was even older. But putting it together in this particular, in applying it to neural networks, this whole combination was actually his innovation. Okay. And this back propagation, simply when it applied over here, it works very well. Okay. It doesn't look like it can work, but actually, when you're looking at the gradients and you're applying this technique, it somehow works. Okay. And we've seen why it works. We have the understanding. But जो आपका सवाल था कि why does it work? Think about it. Gradient descent. All right. Gradient descent is being applied, and then back propagation is being applied through all the layers. So that combination is actually giving the answer. Okay. If you're not convinced, go back. Okay. Look at the entire algorithm and see, try to get an intuitive idea, why is it actually working? But the answer is already there. Okay. In all the discussions we've already had. ठीक है? जी. So it's possible. So it is quite possible that K आपने 16 filters किया and उसमें से 3 filters are doing exactly the same. It's quite possible, right? In fact, if you make too many filters, आपके suppose 15 features देखें, आपके ultimately you have a large number of images. Okay, each one of those images has some distinct features. Okay, for example, as I said, if there are faces, people that are having beards, people that have glasses, किसी के लंबे hair हैं, किसी की मोछें हैं, किसी के नहीं हैं. So these are all features. Now, if your algorithm was very simple, if it was an X and an O, okay, there aren't that many features in that. Okay, and if you use K is equal to 100, what would happen? There would be a lot of duplication. Even though you may have a million images of X and O, ultimately what's going to happen is that आपके जो really distinct features थे, which we know are maybe half a dozen, for O we said that there is about 1, 2, and 3 features, right? For X कितने features थे? There were basically 1, 2, and 3. I think O के 4 features थे and X के 3 features थे. So all in all, there are a total of 4 plus 3, 7 features that we can think of, right? Now, अगर आप K is equal to 100 कर देते हैं, what's going to happen? Let's say not 100. Let's say कि आप 7 features, आप actually हमें पता है कि 7 features होने चाहिए. But you make K is equal to 70. What's going to happen? There's going to be, each of those features is going to be repeated 10 times. Okay, there's going to be a lot of duplication. So, okay, so that's a good question. Okay, आपका जो सवाल है, it's a good question, which is saying that suppose that hypothetically, when you took the random numbers, you got identical numbers, which is very unlikely, by the way, right? Picking real random numbers. In fact, the probability, if you know probability, the probability of picking 2 real numbers which are identical is what? Not infinite. Probability is probability of 2 numbers. You pick 2 absolutely real numbers which are have infinite number of decimal places. Okay, you pick 2 numbers. What is the probability that those 2 numbers will be identical? It's 0. Okay, it's not infinite, it's actually 0. Okay, probability always has to be between 0 and 1. It can't be negative, it can't be more than none, the probability is 0. So actually the probability of picking 2 filters randomly, if it's a proper random number generator, is actually 0. But let's say hypothetically ho jata hai, they're very close. So the question is, will you, even let's say you pick 7 filters and you expect it will come up with 7 different features. Now, suppose that all 7 numbers you आपने जानबूझ करके random number नहीं किया, आपने जानबूझ के सबको 0 कर दिया. Okay. So the question is, will it come up with 7 different filters or not? You quite convinced कि 7 नहीं होगा. आपने क्या इसका practical किया है? Okay. 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 ठीक है. Okay, that's a good thing. I haven't actually tried this, but it's interesting feedback for the class that what you're saying is that if the numbers are initially picked in such a way that the filters are all identical, then what you're saying is that the results are going to be that they're all going to converge to. Okay, so this is something that I'll also test out. I don't know if what you're saying is actually true or not. It could be true. I'm not denying that, but let's all experiment with that. It's an interesting point. Okay. But again, as I said, you're trying to pick filters which are random. Okay, so the probability of that is low, but if you do that, then maybe you have this problem. Achha, so now, so we have an idea why people are picking certain size of filters. अब इन्होंने filters यहाँ पर 22 pick किए. Again, you experiment with different architectures, as we're going to see that people have experimented with a lot of architectures, and then it's a lot of times people say, deep neural networks is actually like a black box. Okay, you don't really know what's going on inside. People experiment and then they come up with solutions. Some things work, some things don't work. So it's a sort of an art. It's not really a science if you think about it. Okay, there's a lot of art that is part of it. Similarly, they've chosen a third layer. Again, they've chosen 20 layers. Okay, now question is, why have they chosen 3 layers with each one of them having 16 or 20 layers, as opposed to picking 1 layer which had maybe 100 features, right? So there's no clear answer to that. The architectures, people experiment and find out which architectures are good and which are bad. Okay, and then after a lot of experimentation, after using a lot of GPU power, people figure out, okay, Google comes up with an architecture which has great results. All right. Similarly, some people, researchers in different universities come up with an architecture which has great results. All right, they publish it, and then people use those architectures and go ahead with those architectures, making modifications. All right, they try to figure out why is this architecture working, what's good about it, and then they use combinations of those architectures. That's how the field progresses. Okay. So this is how, and then there's something called a softmax. We'll talk about softmax a little bit down the road. Okay, hopefully today. So now let's take a look at the results. And before we take a look at the results, let's try to do some calculations. Okay, so let's go back over here. And we'll come back to the results over here. Okay, so now let's take a look at this and try to figure out these numbers. Okay, so we've already seen some of these numbers. We can see that the filter size, what's the filter size over here? That's a trick question. There is no filter size over here, right? Because this is the input. What's the filter size over here? F is 5, K is equal to 16, stride is equal to 1, padding is equal to 2. All right, so this is what, this is the kind of thing that you should be able to look at it and be able to figure this out. F is equal to 2 over here, stride is equal to 2 over here. There is no K because this is a max pool there. What is F over here? 5, size K is equal to 20, stride is equal to 1, and the padding is equal to 2. All right, and so on. So you can fill this out. You can also figure out the size of the activation there. Okay, but let's also try to do this by looking at the results, by looking at the actual cascaded, CNN. So if you again look at it, the first filter size was 5, okay, which means that the filter size over here is 5 by 5, right? K is equal to 16, which means that this is number 1 and this is K is equal to 16. Okay, there are 16 of these. What's the depth over here? Depth over here is 3. The size over here is what is the input size, which was 32 by 32, okay? Plus you had a padding of, I think, 2, okay? So what's the output size going to be equal to? So it's going to be 32 plus 2 or times 2p. It's 2 on both sides, okay? So it's going to be 4, okay? Minus the filter size, which is 5, divided by the stride, which is, stride I think was 1, okay? Plus 1, okay? So what's the output size? 34, 35, 36, 37, 38, minus 5, 33, 33 plus 1, that is 34, okay? 32 plus 4 minus 5 divided by 1 is equal to, where am I going wrong? 31, sorry, 31. So this is 31 plus 3, that's 32, okay? Now, what will be the activation size? The activation size was going to be 32 by 32, right? What's going to be the depth of this? Sorry? So somebody said 1, somebody said 3. Are there any other possibilities? Should it be equal to this? Sorry? It was changed to grayscale. Very good. So actually this output, this single output was for one of these, right? We did this, right, a minute ago. What was the second one? Was that a separate activation map? If the K was 2, then this was actually a separate activation map. Okay, so what should be the size of this, the depth of this? Well, here, what is K? So what should be the depth of this? Right, so the depth of this is now actually going to be K. Okay, so it's going to be 32 by 32 times 16, or W2 by, so the activation map is going to be W2 by W2 by K. Okay. So that's the input for the next layer. Okay. Now let's try to do this. This is the max pool layer. So this is layer number 1. This is layer number 2. This is the pool layer. What is the filter size over here? We just calculated this. It's going to be 2 by 2. What's the stride over here? This is 2. So the filter size is 2. The stride is 2. What would be the output? What's the input size? 32. Is there going to be any padding? No, for the max pool, there is no padding, right? That's already done over here. So max pool, there is no padding, minus the filter size, which is 2 divided by stride is how much? Is 2 plus 1. So this comes out to be 30, 15, 16, right? Yeah, good. So what's the activation size? Now remember the activation, I'm showing it as A12. In other words, it's straddling between the layers, right? Why is it called, why am I calling it A12? And this is my own notation because this is the output of layer 1 and it's the input of layer 2. Okay, so this is just a convenient way that I use. Okay. What's the activation map of size of layer 2, 3? Okay, so this is going to be layer 3. A23 का क्या size होगा? It's going to be 16 by 16. Why? Because this is W2 by W2. This is the size of the activation. What's the depth going to be? 16. Does anybody agree? People agree or disagree? मैक्स पूलिंग में आप क्या कर रहे हैं? मैक्स पूलिंग में आप ये कर रहे हैं कि आपने ये वाला लेयर लिया, ओके, और आपने इसको अप्लाई किया ये फिल्टर, and you got this particular output. So for each layer you have one activation output. Okay, जब आपने ये इस पर ये filter apply किया तो what do you get? You get this. So what is it going to be? The depth is not going to change when you do max pooling. ठीक है? So this is going to be 16, which is simply going to be the earlier k. Okay, ये जो value k है, this is going to continue on over here. Okay. Now the rest you can already do, and I'll leave it as perhaps homework or something like that for you to actually calculate this.